Okay, hello Year 9. So today what we're going to be doing is looking at how we use data to draw conclusions. And to understand this, a conclusion ultimately gives us the scientific model. Now we have looked at this briefly before. For example, when we first started this, we looked at how we were able to model what we think an atom looks like based on evidence from experiments. So we're going to be focusing on that today to begin with. So first thing I'd like to do is in assignments, there is a link to a YouTube clip, which I'd like you to watch. It's about 9 or 10 minutes long. And what I want you to do is once you have watched the video, just in maybe 3 or 4 sentences, no more, so really try and compress it, identify how we use evidence and theories to make a conclusion. Okay, so essentially your task is, just really put up here very quickly, using information from the video, try to explain in 3 to 4 sentences how we make a conclusion. Okay, so that's your task. So you'll need to watch the video first and then try and do that. So pause this lesson here, please, for a moment, and then have a go at that. So 10 minutes for the video and about, 4 or 5 minutes to think up your sentences. Okay, off you go, please. Okay, welcome back. So conclusions. Okay, so a conclusion is basically a summary of what the evidence actually tells us. Okay, so the main thing which I really want you to take from this, the main point is you can only conclude what data shows you and no more. Okay, so if we use this as an example, it's a very simple experiment. We're looking at, say, the electric current and the voltage through a light bulb. What can you conclude from this? Okay, so just pause the lesson for a moment and just have a look at this data and just write down in one sentence, maybe 2 at the most, a very, what this data tells you. What can we conclude about the current related to the potential difference voltage? Okay, pause that and do that now, please. Okay, welcome back, everyone. So the obvious conclusion is simple. A higher current through the bulb gives a higher potential difference across the bulb. As you can see, as the current is going up, the voltage is also going up. So a higher current gives you a higher voltage. However, this relates to bulbs. You've got to be really careful that your conclusion matches the data and does not go any further. For example, some people might say there's a direct link. Well, we don't know that yet. Okay, you can't conclude the potential difference across any circuit component will be higher for a larger current. The results might be completely different. So, for example, this is for a bulb. What if I put, say, an electric motor in there, or another component like a diode, or even just a resistor? Would I get the same information? I can't say for sure that I would. So you've got to be really careful. You also need to be able to use your results to justify your conclusion. Okay, so the potential difference across the bulb was 9 volts higher with a current of 12 amps. Okay, so for example, 4 up to 13 was a difference of 9 volts. Okay, compared to a current of 6 amps. So as the current is basically what you must do is back up your conclusion with the information. So at 6 amps, the voltage was 4. At 12 amps, the voltage was 13. So an increase of 6 amps gives you a voltage which is 9 volts higher. Okay, so you need to back up your sentence with evidence from this. Okay, so actually once more I'm going to ask you to pause this and add in some data to back up your conclusion. Okay, welcome back. Now, the final thing you need to make sure you do is when writing a conclusion, you must refer back to the original hypothesis and say whether the data supported it or not. So the hypothesis for this experiment might have been that a higher current through the bulb would increase the potential difference across the bulb. So if the data supports the hypothesis, so basically, does the data support the hypothesis that as you increase the current, the voltage will go up? The simple answer in this case is yes. Okay. Okay, welcome back. Now, you might remember these two graphs from a couple of lessons ago. Don't worry if you don't, I'm just using them as examples. So what it shows here is that the independent variable, the thing we changed, seems to have an effect on the dependent variable, the thing we measure. There appears to be correlation. So as one thing goes up, it causes something else to go up. We get this. If something goes up, it causes something else to go down. Okay. So if two things are correlated like this, there's a relationship between them, it doesn't necessarily mean that a change in one variable is causing a change in the other. It's really, really important that you remember this. Correlation does not mean cause. Because this is changing, as this increases, okay, there are three possible reasons why this could be happening. Okay, so we're going to go through them. First one, you need to write this down, is chance. Okay, so it might seem strange, but two things can show a correlation purely by random chance. Okay, so this might be going up, this might be going up, but it should seem that there is a very definite pattern, but it could be down to a total fluke. For example, one study might find there is a correlation, say, between people's hair color and how good they are at frisbee, but other scientists don't get a correlation when they investigate it. The results of the first study are just a fluke. Okay, and it's important. There could just be these random chance events, and even though there does appear to be a correlation, you've got to be really hard on yourself and say, well, how likely is this? Or could it just be down to random chance? For example, you flip a coin 10 times, sooner or later, you'll get 10 heads in a row. Now, the chances of that happening are really low, but they could happen. And so you could say your conclusion might be the coin is weighted, but it's not. So you've got to be really careful when making conclusions. Okay, so can you please write down in your own words what we mean by chance? Okay, so the video and do that now, please. Okay, welcome back. Now, the next possibility is that a correlation might be caused by a third variable. So a lot of time it may look if there's a change in one variable is causing a change in another, but it isn't. A third variable links the two things. So let's just take an example. I've made a quick change to this graph, and you can use this as an example. You can literally just do a quick sketch like this in your book. So you've got temperature going up, and you've got the number of shark attacks going up. So, for example, there seems to be a correlation between water temperature and shark attacks. As the temperature gets warmer, there are more shark attacks. But this isn't because warm water makes the sharks go crazy or anything like that. Instead, they're linked by a third variable, the number of people swimming. I mean, let's be realistic. More people swim when the water's hotter, and with more people in the water, you're going to get more shark attacks. Okay, so it could be linked by a third variable. So once again, pause the video, write down that, maybe just quickly copy that into your book, and then explain using the example of shark attacks what I mean by linked by a third variable. So temperature doesn't mean you get more shark attacks. What is the third variable that links them? Okay, so pause the video and do that now, please. Okay, welcome back. Now, the last reason could be that there actually is a cause. Okay, so cause does mean effect. So sometimes a change in one variable does cause a change in the other. So I've changed the example again. You can only conclude that a correlation is due to cause once you've controlled all the variables that could, that could be affecting the results. So, for example, if there's a correlation between smoking and lung cancer, the more cigarettes you smoke, so the number of cigarettes going up, the greater the risk of getting lung cancer. This is because chemicals in tobacco smoke cause lung cancer. This conclusion was only made once the other variables, such as age, exposure to other things that cause cancer, had been controlled and shown not to affect people's risk of getting lung cancer. So, in order to demonstrate a cause, you must be able to control as many variables as possible. Okay? So, once again, what I'd like to do, the third factor which could affect whether or not correlation means cause is the fact that there is a cause, but the only way to do that is to control as many variables as possible. So, one more time, pause the video and write down what do we mean by cause. So essentially, there is a link between one variable, your independent variable, affecting your dependent variable, but only after you've controlled as many variables as possible to reduce the risks of random chance or it being linked by a third variable. Okay, so pause the video and do that now, please. Okay, welcome back. Now, in assignments, there are two worksheets I would like you to try, and what they're designed to do is test, can you use data to basically make conclusions, just like you've been shown. However, before I do that, I just wanted to introduce this. Now, this talks about uncertainty, and uncertainty is the question mark over all our science experiments. And this is really good because this covers biology, chemistry, and physics. So in science, when we get data, we need to know how wrong it could be. So we check this by testing the uncertainty. So let's just say we were measuring the speed of something here. We did it 5 times, 1, 2, 3, 4, 5, and then hopefully you know how to calculate a mean. We add them all up and divide by 5. So let's just very quickly bring in a calculator. So hopefully we can do this. So 2.01 add 2.67 add 2 add 2.45 add 2.98. Okay, so that equals 12.11. We divide it by 5 because we've got 5 results, and our average is 2.422. So our mean is 2.42. Okay, just rounded. So there it is. Okay, but here is the question. That's our average, our mean. The uncertainty, look at this range. We went as high as 2.98, but as low as 2. So there's a whole numbers difference, nearly 1 difference between our highest result and our lowest result. So how confident can we be of this value of 2.42? Well, there's a method you need to work this out, and absolutely you'll need to know this. Okay, so to find the uncertainty, first you find the range. So in this case, the lowest value is 2 and the highest value is 2.98. So our range is 0.98 because that's the difference between 2 and 2.98. It's 0.98. And the way you find the uncertainty is like this. The range divided by 2. Whoops, just move that down slightly. So in this case, it's 0.98 divided by 2 equals 0.49. So basically, we can be pretty confident that whatever results we get, they're not going to be more than 0.49 out from this value of the mean. And indeed, they're not. So this is a really key thing that you need to put. So in your book, I suggest you use this example. So you're probably going to need to copy part of this page. And this is the really important part here. okay, the method for calculating the uncertainty. It's the range divided by the 2. So the range is your highest value minus your lowest value, so 0.98, or the difference between your highest and lowest value, divided by 2, and it will tell you how wrong could you be, which is acceptable. Okay, so one more time, pause the video and copy this down, and then as soon as you've done that, okay, you can have a go at the worksheets, okay, and I will try and upload the I will upload the answers for you at the end of the lesson so you can check to see how you've got on. So good luck, and I'll be online as always to help you if you need.